we had seen that if you want to calculate such endpoint function in the exact theory, this was given by this function where all these operators should be calculated in the non-interacting theory. Now this, okay, let me add the connected part because there's the denominator which cancels all the disconnected pieces. Now what does this mean? So we just have an expansion, sum over n, we have I to the n over n factorial, product over I, dxi, d4xi, and then we have 0 and ln x1 L interaction xn. So we need to calculate this one. Well, the n goes from 0 to infinity. Okay, one thing is there are infinitely many terms. Even if you don't go and calculate infinitely many terms, what happens is as n increases, the number of diagrams increase really fast. You should have probably felt that in your midterm. Even in the second order, there are many, many diagrams. If you go to third order, I mean, in fact, the number of diagrams increases factorially with the order. So what you do, you cannot calculate all of these terms. So what you do is you just calculate the contribution from n is equal to 0 plus the contribution from n is equal to 1 plus, if you are lucky, the contribution from n is equal to 2, and you just cut it there. Now, still, what you want to calculate is not the sum. What you want to actually calculate is this matrix element, at least approximately. But if this matrix element is approximately given by this term, it basically means that n is larger, the terms for n is equal to larger than or equal to 3 should be much, much less than, let's say, the contribution from n is equal to 2. If this is satisfied, then you just calculate up to n is equal to 2, and the rest will be much smaller, so you're happy. For example, an idea of this is...
But you said that, for example, in QSC, that does not work. Because
yes, let me just continue with that one, and then I will come to your point. An example, let's say 1 plus x to the power n. What is this? This is 1 plus nx plus n times n minus 1 over 2x plus etc. So let's do an example. Let's look at 1.1 squared. What is 1.1 squared? 1.21. This is the exact number. Well, let's see. Let's write that as 1 plus 0.1 squared, which will be 1 plus 2 times 0.1 plus 2 times, sorry, this is n times, no, 2 times 1 over 2 times 0.1 squared. Well, this is not an infinite expansion, but you see already if you cut it from here, you calculate the first correction. What you get is 1.2, which is not bad. Let's say, what about 1.1 squared? This is 4. But if I write that as 1 plus 2 times 1, and ignore the rest, then that expansion tells me that it is 3. Now you see, in this example, the error I introduced by ignoring all the remaining terms is 1%. In this example, The error I introduced by ignoring the remaining terms is already 25%. And I don't know if you, let's say, you can just, this is one example where just cutting at a finite number of terms in your expansion, not calculating all of them, will definitely introduce an error, but depending on your various contributions, that error might be very small or might be very large. If it is very small, great. One case where it is very small is electromagnetic interactions. The fine structure constant, if you calculate the fine structure constant, remember this is e squared over 4 pi, I think there's also h bar c. This is 1 over 137, or of the order of 1%. So if you take the square of it, it will be 10 to the power minus 4. If you take the cube, it will be 10 to the power minus 6. So higher orders in this electromagnetic fine structure constant will give you a very, very small number. So you can safely ignore after calculating the first or second non-trivial correction. The rest will be really very, very small. They will change the digits at the far end. But for strong interactions, this is of the order of 1. So how can I say that just calculating 1 or 2 terms should be enough? I cannot do that. So I have to calculate more and more terms. Now, what does the Schwinger-Dyson equation tells me? It tells me, for example, this matrix element is given by, well, now I don't remember the exact expression, but let's say the free Feynman propagator it should be something like this. Well, as you said, this looks like the perturbative expansion. I can actually derive the perturbative expansion from this equation. But then, if I do that, then I'm back to this problem over here with the perturbation theory. Now the question is, if I don't do the perturbative expansion, what sense will I make out of this? That's a different problem. But if somehow you can make sense out of this, for example, what you can do is claim that, I don't know, 10-point functions are negligible, ignore them, cut everything above 10-point functions. Then this would give you relationships exact relationships between the lower order point functions, 2.4, 0.6, etc., depending on your theory, what your L prime is. Then that is a finite number of equations that you might try to solve. That's the advantage of this one. Or you can, depending on the physics you have, you can say that maybe the endpoint, you can guess the form of the endpoint function, the 10-point function. If you can do that, if you can somehow, well, you see, this is a relationship between various point functions. There are infinitely many of them. But if you can somehow predict the form of your functions at higher point functions, let's say, then this will be exact. You are not doing any perturbative expansion there. You had a second question?
Yes. Do these
yes.
Do these endpoint functions or the Wick's theorem, do they exist outside of quantum field theory as a separate field or as a subfield of mathematics, like in topology, or
well, you see,
maybe taken out of context of quantum field theory?
Well, you see, what we are calculating, the things we are calculating averages somehow. In statistical physics, you have almost exactly the same theorems for statistical averages, statistical covariances, etc. Or here we are drawing Feynman diagrams. They look like nuts. So mathematicians using knot theory, they try to enumerate them, find the number of them, the independent ones, etc. In statistical physics, we have a similar expansion, basically. Mathematicians were using path integrals for quite some time now to study functions or topologies. Now, there are uses, there are techniques that say inspired by physicists. For example, Witten received the Fields method, which is like the Nobel Prize for mathematicians, because he solved some problems using physics intuition. He solved some problems that the mathematicians couldn't solve for quite a long time. Other questions? So today, let's start with spin. Now, I will eventually be studying spin on objects. But before that, let me ask you, what is spin? What do you know about spin?
I'm not playing this again. You do this every semester, you get the wrong answers. So.
No, come on, there's no wrong answer. I just want you to understand what you know so that I can fill some gaps. Come on, you have heard of spin, right? Spin of objects. You have probably studied the spin in spin of an electron in a magnetic field. There's the spin-spin coupling, spin-orbit coupling. The electrons has spin 1/2.
Interesting quantity determining the nature of the object particle.
So what does that mean?
That's a quantum number you need to add to angular momentum to get the total angular momentum.
And it's related with the magnetic field.
Let me start by saying that it's not related with quantum mechanics.
It's related with magnetic field, right?
No, not even magnetic.
The lowest order representation of the...
It's related with rotations.
Yeah.
So let me first prove that.
It's a representation index for the Lorentz group.
So what does that mean? Let's look at rotations. We looked at scalar functions. I will claim that they have spin 0. How do I know that they are spin 0? Well, let's see. Let's see how I rotate these functions. I will consider rotations around the z-axis all the time, but generalization to any other axis would be kind of trivial. Just so I will be drawing these two-dimensional pictures, but remember, it's a three-dimensional problem. And here in this space, I have, let's say, I have some function. Let me use this notation for the time being. P is any point, some representative point in this space. I just rotate everything. Let me use the active point of view of these rotations. I will be rotating the universe, not my axis. You can also do the same thing if you are rotating your axis, but let me just rotate the whole universe. So what will happen is this point P will move to this point over here. Let me call that P prime. And of course, in this new rotated system, I have a different function, phi prime. But I know the value of this function at the point P prime, which will be phi of P. The value of this new rotated field, the value of that at the point P prime is just the value at the point P, which was my point before the rotation. Now, let me use the coordinates. The point P has coordinates x, y, and z. The point P prime will have coordinates x prime, y prime, and z prime. And of course, they are related. So what is x prime? Let me call this rotation angle theta. Well, x prime will be x cosine theta minus y sine theta, and y prime is y cosine theta plus x sine theta, and z prime is equal to z. Or I can invert this also. X will be x prime cosine theta plus y prime sine theta. Y will be y cosine theta minus x sine theta. Z prime is equal to z. By the way, this phi is just some arbitrary mathematical function. I'm not doing physics at the moment. I'm just defining some functions and see what happens, how they rotate. Well, what is now phi prime, x prime, y prime, z prime? As a function of x prime, y prime, z prime, I said that this is phi of p, phi of x, y, z. This is phi of x prime cosine theta plus y prime sine theta. And these are primes. Y prime cosine theta minus x prime sine theta, and z prime. In terms of x prime, y prime, and z prime, this is my new function. Well, a finite rotation, I can always imagine it rotating small by very small angles many times. So let me look at the case where theta is much, much less than 1. I take a one very small step. That means, well, let me also get rid of these x prime primes, because I already expressed everything in terms of these new coordinates. Phi prime at the point x, y, z will be phi at x plus y theta, and y minus x theta, and z. This is the definition of my new function. Well, theta is very small, so I can just expand it with respect to theta. Plus, of course, there are corrections of the order of theta squared. This will be phi of x, y, z plus, let me take the derivative of phi with respect to the first argument, which is x. The change in x is y theta plus derivative of phi with respect to y, the second argument, times the change in y is minus x theta plus terms of the order of theta squared, which I can write as 1 plus theta y del over del x minus x del over del y plus terms of the order of theta squared act as an operator acting on my function phi of x, y, z, which I can write as the exponent I theta, no I. The exponent theta y del over del x minus x del over del y plus corrections of the order of theta squared. And let me call that thing this is an operator that acts on my function phi x, y, z. Now an arbitrary rotation around the z will be just rotations by, let's say, theta over n. At each step I rotate by theta over n, but I take n steps, which will be exponent of theta over n y del over del x minus x del over del y, plus some possible corrections of the order of theta squared, which is now theta over n squared raised to the power n. But I should also take the limit as n goes to infinity. I have infinitely many infinitesimal steps. But this is exponent theta y del over del x minus x del over del y. So my wave function, my function, after rotations takes this form, by rotations around the z-axis. This is my new function after I rotate it. Well, usually, you see, this is an anti-Hermitian operator. If you take its Hermitian conjugate, you will get a minus sign. Well, we prefer Hermitian operators to anti-Hermitian operators, so let me write it in a slightly different form. Does that look familiar to you? This operator. It's what we call in quantum mechanics the z component of the angular momentum operator. You see, here I am just looking at mathematical functions and how they behave under rotation. There is no quantum mechanics. Now, what quantum mechanics does is it tells us that we should describe our systems using functions. So once you do that, whatever property your functions have, your system should also have, because we are using functions to describe our physical system. And basically, these angular momentum operators uniquely specify how my system rotates. And nothing else. I don't need anything else. Well, you can just generalize it to rotations around the y-axis, rotations around the z-axis. You will basically get the other components of Lx, Ly, and Lx and Ly, your angular momentum operators. So any questions up to here? Now, still, there is nothing that says that it's a scalar, it's a spin 0. We didn't yet define what spin is. Now let's look at what happens if instead of a function that assigns a number at every point, you see phi is a function that assigns a number at every point. It can be a complex number, real number, whatever. It's a number. It doesn't have a direction. Let's assume that now, yeah, there's a minus in between. Now let's look at what happens if our function also has some direction. This is my x and y coordinates. Here at this point P, I'm defining a function that would assign a vector to the point P. Now the vector will be, let's say, pointing in some direction. It can be an arbitrary direction. So this is, let's say, V. This is my function. At every point in space, it assigns a vector. Well, it doesn't have to be vertical. It can be in any direction. This is what we call a vector field. It assigns a vector at every point. Now let's imagine I rotate this whole thing. If I rotate the point P, now that point will be here. This is P prime. But while I'm rotating my wave function, I'm also rotating the direction. Now it is pointing in this direction. So if this is the direction of V of P, this is the direction of V prime at P prime. You see, V prime at P prime is not just V at P. Now compare it with this one. My function at the point P prime, my new function at the point P prime was actually equal to the previous function at the point P. But now I don't have that equality. Basically because V prime of P will be equal to V of P, but I also have to rotate the vector. So let me write it. I'm not just rotating the coordinates, I'm rotating the vector itself. So there are two things that I have to consider. One, the rotation of the coordinates. The other one, the rotation of the vector itself. Well, I can actually, I have actually calculated what V of P is. This is V of P prime e to power minus I theta Lz. Are you convinced?
Well, we just put the Lz rotation of the the scalar function to the vector field, but their components have.
You see, the components are still here. You see, V has, let's say, the x component at the point x, y, and z. You see, here what I did, I have this scalar function, phi prime x prime at the point x prime, y prime, z prime is actually phi of x, y, and z. Then what I did, I expressed x, y, and z in terms of x prime, y prime, z prime, and just proven that phi of x prime, y prime, z prime, so phi of x, y, z is actually equal to e to power minus I theta phi of Lz x prime, y prime, z prime. This is what I had proven for any function phi. Now you see here I have Vx of, for the new point, I have Vx of x, y, z. Well, I can express this as Vx of, I can express x in terms of x prime, y prime, z prime, y in terms of x prime, y prime, z prime, and z in terms of x prime, y prime, z prime. I can basically do the same thing I did before. I'm not rotating in. This is Vx, is just a number. So this will be just e to power minus I theta Lz Vx of x prime, y prime, z prime. But I'm not yet done. To calculate my V prime, it's not just Lz.
And the SOT thing.
I have to calculate this one also. How do I rotate just ordinary functions, ordinary vectors? That is the next step I have to do. There's an additional component, additional thing I have to do. Well, let's calculate that one. You see, let me just choose an arbitrary vector. You see, this is my vector A. I'm rotating it by theta. This is my A prime with different components. Now, A prime, the x component of A prime, will be the x component of A times cosine theta minus the y component of A times sine theta. Ay prime will be the y component of A before rotation cosine theta plus the x component sine theta, and az prime will be just az. So a prime x, a prime y, a prime z is actually cosine theta minus sine theta, sine theta, cosine theta, 1, 1, no, not 1, 0, 0, 0, 1, 0, 0, 1. This is my weird RZ of theta. Well, I can write it as an exponent also. I can basically do my earlier trick. I can calculate RZ of theta for a very small angle. For that very small angle, my function will be 1, 1, 1 minus theta, theta, 0, 0, 0, 0, which is the identity, 3 by 3 identity, plus theta, 0 minus theta, theta, 0, no theta, 0 minus 1, 1, 0, 0, 0, 0, plus higher order terms. For an arbitrary rotation, or let me, before that one, which is equal to exponent of theta times 0 minus 1, 1, 0, all these zeros, plus terms of the order of theta squared. This expression and this expression agrees up to order theta. I'm actually calculating everything up to order theta. So there are all these corrections of the order of theta squared. Now, to go from this expression to this expression, you can just say that I'm taking the logarithm and putting whatever the logarithm I have in the exponent, and then Taylor expanding the logarithm itself. So all the theta squared corrections I can actually put in the exponent. So let me see, before I defined minus I theta, so this I can define as exponent of minus I theta. Let me call that thing SZ, plus corrections of the order of theta squared, where S...
The consequence of the exponential wouldn't be directly, theta matrix, why we write the, theta squared, higher order term as a, exponential, like the Taylor expansion did not go like that, theta squared, theta something, exponent.
Okay, so.
Whatever.
Hocam, I think I understood. Didn't you get rid of the modulus terms of theta squared and convert it to exponential?
Not, I didn't yet. You see, I'm just, for the time being, I'm just expanding things up to order theta squared for very small theta. I'm just calculating this one. I'm writing that one of the order of, for theta very small. I know that it is such an expansion. I don't know what theta is, what that of the order of theta squared terms are. They will turn out to be 0. But I don't know that yet. The only thing I know is RZ of theta, which is this matrix over here. By just Taylor expanding in theta, I know that I can write it as the exponent of minus I theta S of Z plus some possible corrections of the order of theta squared. Now I do, SZ would be, let me also write that down, 0 minus I, 0, 0, 0, 0, 0, 0. And now I can write RZ for an arbitrary theta. This will be RZ for theta over n raised to the power n in the limit as n goes to infinity. And this will actually turn out to be exponent minus I theta S of Z. Now, I just skip some steps. So those of the order of theta squared terms are not actually there. Now, what is this sz squared? Well, let me calculate its square. This is equal to 1, 0, 0. Zero, 1, 0, 0, 0, 0. So this already tells me that eigenvalues of sz at least their square is 1 or 0. So sz can have eigenvalues 0 plus or minus 1 because their square has to be either 1 or 0. And trace of sz is 0 from here. So I definitely know that without calculating the determinant, etc., without solving the eigenvalue equation, I know that sz has one eigenvalue plus 1, another eigenvalue 0, another eigenvalue minus 1. So what happened? I have now a vector field. I rotate this whole thing, and I have after a rotation, I get a new vector field, which I can express in terms of the old vector field by multiplying it with this operator. So just applying Lz is not enough. I have to do some additional thing in order to rotate this vector. That is called the spin. That extra factor is what we call the spin. Now, if we go back when we were looking at this phi, well, Lz was enough. There is no s needed. So we say that the scalar functions are spin 0. Now, I looked at the vector function. Now, when I look at the vector function, just the angular momentum is not enough. I have to do more. I have to rotate this direction of this vector, and that additional thing is what we call the spin. So the sz at least has eigenvalues plus minus 1 or 0. Well, you can go ahead and calculate sx and sy. Just consider rotations around the x-axis, y-axis, z-axis. And you can actually show that sx squared plus sy squared plus sz squared will be just 2 times the identity. And this 2, by the way, is 1 times 1 plus 1. Again, this is just a property of functions, just ordinary functions in mathematics. Now, once you identify your physics with functions, your physical systems, once you start describing your physical systems in terms of your functions, whatever property the functions have, your physical system should also have. So if your functions have a spin 1, then the corresponding particles are what we call spin 1 particles. So if you know how a function behaves under rotations, that means if you know what this operator is for your function, there will always be some Lz over there, but there will be additional parts. Then you can determine the spin of the particle that that function describes.
Is it not just a mathematical description of the spin?
Sure.
If someone asks, we are physicists, right? And spin all the time is something quite interesting thing to ask. And if someone asks me what is spin, do I just say that we are just transforming the vectors? I mean,
No.
am I not supposed to answer such a Schrödinger experiment or something?
Sure. I mean, you see, the thing is, at least once you claim that, okay, to describe your physical system, you will use functions. Once you make this identification, then your functions have this property called spin. Those are, as you said, they are the irreducible representations of rotations, by the way, not Lorentz group. We have the irreducible representations of the Lorentz group. Then the problem is, do they have any physical observable consequences? Like, do these particles interact with magnetic field if they have charge due to their spin? Of course, if they have angular momentum, they will interact with the magnetic field. But even if they don't have angular momentum, orbital angular momentum, they will still interact with the magnetic field, it turns out. So then we have this Stern-Gerlach experiment and other physical consequences.
The point vector is a photon and it has spin 1 symmetry, so it is not SO3 or SO1, it has symmetry.
So that is our problem now. We just don't want three-dimensional rotational symmetry. We want Lorentz symmetry. That causes kind of a problem because we want to describe everything in terms of Lorentz vectors, not just three vectors. So if you take a Lorentz vector, it has a zero component, time component, and space component. Under rotations, this transforms. That's a spin 1 object. But this doesn't change. Well, of course, if it depends on x, y, and z, that will change due to the angular momentum operator. But that will be the only change. V0 will not have that s component. So what we say is a Lorentz vector is actually a spin 1 object and a spin 0 object.
Lorentz vector 4 vector, right?
Plus a spin 1 object, yeah. A 4 vector has a spin 1 component and a spin 0 component. Now that will be kind of problematic. That is a problem that I should address because I would like to be able to write down a theory that will describe only spin 1 objects. I don't want to add that additional spin 0 object in my theory. My theory I should be able to write a theory for spin 1 objects only without using any spin 0 object. Now, one thing, one step at a time, let's say. First, let's try to generalize this to Lorentz symmetry. You see, I'm just looking at rotations. Let's say that I have a wave function describing an object at rest. So I can just look at how the wave function changes under rotations and tell whether it is a Lorentz spin 1 object or spin 0 object. But if the particle is moving, if I want Lorentz symmetry, I should be able to carry out this discussion in any reference frame, not just the reference frame in which the particle is at rest. So in that case, we should basically make a distinction between particles. So those particles whose p squared is equal to 0, massless objects, and then particles which has a mass. If a particle has a mass, I can always say that, I will go to this rest frame and I will consider rotations, in how it behaves under rotations in its rest frame and determine whether it's a spin 0, spin 1, etc. If I don't want to choose a preferred reference frame, that is what I would like to do. I would like to have my discussions in an arbitrary reference frame. So let's first look at this one. Well, in rest frame, I want to avoid the rest frame, but let's learn some lessons from the rest frame. P is just M and 0. So in the rest frame, rotations do not change P. In an arbitrary reference frame, I can consider Lorentz transformations that keep, that, let's say, leave P invariant. I will not consider any Lorentz transformation, but I will look at the behavior of my particle under Lorentz transformations that leave P invariant. No, not the vector P. The 4 vector P invariant. If I go to the rest frame, they are just ordinary rotations. There will be kind of some generalized rotations in an arbitrary reference frame. This is called the little group. Whatever I did before, I can do with this little group. They are nothing but rotations in rest frame, boosted. But now I have a problem in the case of P squared is equal to 0. There is no rest frame. So since there is no rest frame, let's say that I can still look at Lorentz transformations that leave P invariant. Let me still, to get some lessons, let me still choose a reference frame in which P will be E 0, 0, E. This is my P. P squared is 0. This is a 4 momentum. I'm choosing my z-axis in the direction of the space component of this 4 momentum. Now, the Lorentz transformation that leave P invariant are nothing but rotations in the xy plane around the z-axis. I don't have the full rotational symmetry. I just have a smaller rotational symmetry to classify my particles. I'm not going into too much details because to be honest, I actually don't understand every detail, but the only change is Jz. Let me use the Jz. The spin in the z component can only take 2 values, plus or minus J. It only has 2 polarizations. In the massive case, Jz can take values plus minus J, plus minus J minus 1, etc. Let's say up to 0, down to 0. J can be also 1/2. For
J total angular moment?
J is the angular momentum, the spin of my particle. But for massive particles have all these polarizations, has 2J plus 1 different polarizations. But the massless particle only has 2 polarizations, independent of total spin. For example, photon, which is a vector particle, it's massless. It only has 2 polarizations. It doesn't have 3 polarizations. But W bosons, or Z, they are vector particles, but they are massive. So they have all 3 polarizations. Rho meson is a vector particle. It also has all these 3 polarizations. So if we are to write a theory of vector particles, we should be able to explain all of this or take this into account in our theory. So any questions? We will write our theory in the next hour. Then let's give a 10-minute break and we will continue.